Okay guys, in this video we're going to look at finding the midpoint between two charges that is effectively a field of zero. So we're going to start out with a charge here of Q1, we'll call this Q1, and then we've got another charge over here of Q2. I'm going to say that Q1 is 4 microcoulombs, and we're going to call Q2 6 microcoulombs. And for ease of calculation, we're going to say that the distance between these two is 1 meter. So we've got a distance of 1 meter between a 4 microcoulomb and a 6 microcoulomb charge. So what we want to find out is a position in between these two charges that has effectively zero field. Now, that zero field comes about because when you draw the lines, and you will have likely seen these field lines in lessons or drawn them already. If not, go back and have a look at the previous videos to see them. But there's going to be a point in between this field, actually closer to the 4 microcoulomb charge, that effectively has a field that is equal to 0. That's because the field strength from the 6 at that point is equal to the field strength from the 4 at that point. Now that's really important because we can then say that E for Q1 is equal to E for Q2 at that point, because they've got to be equal and opposite. So if this is a positive charge and this is a positive charge, apologies, I didn't say that already, but they're both positives, and they're both effectively, if you were to put a test charge, a positive test charge in this field, at that point, it wouldn't go anywhere because the field strength pushing it that way is exactly the same as the field strength pushing it this way. So, we've got this idea over here that E1 is equal to E2 at that point right there. And because we're from lessons, we know that or the previous video, that the field strength of an electric field is equal to KQ over R squared, where K is 1 over 4 pi epsilon naught. Now, this is just a term that equals K, and epsilon naught is the permittivity of free space. Obviously, if you're not in a free space, then you don't want to use the permittivity of free space. You'll use a different value. But for all intents and purposes, we are going to accept this value as 8.99 times 10 to the 9. And that's what this would work out as, is using the permittivity of free space here. So all is well in that instance. And that's what we're going to use. So, so we have a calculation over here that we can then write down, that KQ1 over R squared is equal to, now before we do that other side, let's just look at what we're talking about here. R squared is going to be the distance from here to that point in the field. So that's R here. Well, there's a problem because we can't use R again on the other side. So we can do KQ2 over, well, I can't put R in there because R is this distance. The R for here would be from there to there. We can't use R again, so we've got to use something else. Well, what we can use is the fact that we know there's a meter here, and that the distance from there to there is R. So we can say that 1 meter minus R is going to be our distance from there to there squared. So this is all coming together quite nicely now. So we've got a term that we can use for our calculation. And we can do a bit of algebra. So we can then get to a bit of algebra. We can get rid of the k's because they would cancel out by dividing both sides by k. Then we end up with 1 minus R squared over R squared is going to equal Q2 over Q1. And then we can do more algebra. We can square root both sides. So we end up with 1 minus R over R is equal to the square root of Q2 over Q1. So all is well so far. We've got 1 minus r over down here. Probably didn't need the brackets really, but over r is equal to square root of Q2 over Q1. We could do some more algebra. 1 minus r is equal to square root of Q2 over Q1 times by r. Then we can take it a step further. We'll go up to the top now. So we want to kind of get rid of these two values of r, because we really want one lot of r, don't we? Because the whole purpose in this is finding out where in this midpoint between here is this point of zero field. So 1 minus r equals root Q2 over Q1 times by r. So we need to do a bit of algebra to help us out with this one. So we can then say that 1 is equal to square root of Q2 over Q1 times by r. Okay, I'm going to put that in brackets right now. And obviously I've moved the r over, so this r is going to become plus r. Okay. So if I've got plus r, well, what I've really got there is plus r times 1. And actually what we've created now is a situation where we can see the common factor here. Well, look, we've got r times by that one, r times by 1. So what we can do is we can factorize these, and we end up with 1 is equal to r Q2 over Q1 plus 1 is going to equal 1. Remember, this 1 is the 1 meter that's all the way from the starting point over here. And this 1 is just a 1 that I've created because I've got one lot of r that I'm adding on here. So what we can say is, we can then say that r is going to equal 1 divided by root Q2 over Q1 plus 1. And effectively now, it's just a matter of plumbing in all the numbers. So I can plumb in all these numbers, and I can quite nicely see that when I put in all of these numbers, so root Q2 is going to be 6 over 4. Now you might be looking at this and going, wait, you've missed the micro. No, I haven't. I've just realized that I can cancel both the micros in each case. So times 10 to the minus 6 times 10 to the minus 6, those will both cancel in this instance. Plus 1. And when we work that out on our calculator, give me a moment while I work this out on my calculator. I can't do this math in my head. We get an answer of 0.449. So 0.449, which for all intents and purposes is 0.45 meters. So we're saying that the distance r from there to there is 0.545 meters. Therefore, retrospectively, the distance from there to there is 0.55 meters. So from there to there is 0.55 meters. And it's as we would expect, because the greater charge would exert a stronger field than the smaller charge. And so a 0 point would be further away from the stronger charge and closer to the smaller charge. Now, some of you might consider doing this a different way for this step right here, and I'll just show you that here just to show you how you can get the same answer, maybe slightly easier without having to do so much algebra, because this step might be a bit foreign to some people. It shouldn't be, but it might be a bit foreign. So I'll give you a heads up on where you could do this slightly easier. So let's just jump back down from this point here. And effectively, at this point, you might just decide to put the numbers into this value right here. So you end up with 1.22, because this value equals 1.22. So you end up, that equals 1.22r. And then you can say, because you've rearranged this value to be to come over here when we brought this one over here, we can say that that one there is equal to 1.22r plus r. Well, and then you might find this easier to see than this, because you might go, okay, 1.22r plus r, well, that just means that I've got 2.22r. And that might be easier for some of you to see and see how that works there. I know I like that a bit better by working out the calculation of 1.22 sooner rather than doing all the algebra here. I quite like to do this because it makes it very simple to see straight away. You know you've got 1.22r plus r, which is basically 1r. That means you've got 2.22 lots of r. Which will equal 1. And then the calculation, just to carry on from that to get the same answer, would be 1 over 2.22, which equals r, which in this case would still equal that 0.45. So all is well. Either which way you would like to do it, it doesn't really matter. As long as you get the right answer, that's all that matters. We're going to have a look at a few variations on this in class, but do make sure you understand what the algebra I've been through here at the very least. And if you want to, if you're more mathematically inclined, you might want to try and get your head around this way, but for most of you, you will look to try and do it this route here. Okay? We'll talk about this in class and we'll do some variations.